In this video, we will look at some experimental data that takes us from the Rutherford model of the atom into the Bohr model of the atom, which is a little bit closer to what our current model looks like. So, starting with an example that is not actually for an atom, but to relate it to something that you know, if you had a prism and white light was passed through a prism, what you would see is a continuous spectrum in the visible region, like this rainbow of colors. So this is what happens when any kind of light goes through a prism and you see a rainbow. So when light is put through a prism, it gets bent in a specific way, and this is why we're seeing the continuous spectrum. If instead you have a light source that's atomic, so think something like a neon sign. So a tube usually that's under vacuum, which means like there's absolutely nothing in it but the neon. And if we can get that to light up and we put that light through a prism, we instead get an emission line spectrum. So the colors don't blend together. We do see lines in specific color regions and even some that are outside of this visible color region, but it is a line at a very specific wavelength and energy. These lines come from the emission of a photon, which is what you get when you have an excited atom that releases energy. The line spectra are unique for each element. So we can take two line spectra, and if they're different, know that they're different elements, and in a lot of cases, take the pattern in the spectrum and where the lines show up and use it to identify an element. So the lines always show up at specific wavelengths, and then the example that I have here is for a hydrogen atom. The lines that we see, so my scale here is just a wavelength scale. There's a line at 656 nanometers. So that 656 nanometer wavelength, you know now how to calculate an energy associated with that. That nanometer value corresponds to the color wavelength energy of the photon, one of the photons emitted from the atom. We also see a set of lines at 486 nanometers, and then also a bunch of closer together lines around 434 nanometers. So with this kind of data, and building on everything that he had to work with going into it, Bohr came up with these postulates. The first was that atoms can only exist in fixed or stationary, discrete energy states. So it can be at this energy, and it's going to stay at that energy unless we do something to it. And if we do something to it, it will go to some other fixed energy. The transitions between those energy states are sudden, and they are quantum jumps. So it is at one state, and then it jumps to the next state. There's no gradual transition. There's no in between. It can't land anywhere in between or anything along those lines. So, and I have in here in parentheses, the electron does the jumping. So what we are going to see is that we'll put some kind of energy into an atom. An electron will go from wherever it was, it'll go up, it'll absorb that energy, go up to a higher energy state. And then when it drops back down, that's when the photon gets emitted, and the photon is what we can detect. And then the third postulate is just, really more of a reminder that like conservation of energy holds. So this is great because it means that when we get photons out, that energy has to be equal to whatever energy was put in. So the change in energy for an atom is equal in magnitude. We're going to have some signage issues. It's equal in magnitude to the energy of the photon absorbed or emitted. So if it absorbs a photon of a specific energy, the electron has to make a jump that is that amount of energy. Okay, there are two ways that we can show these electron jumps and energy transitions. So the first way is on this sort of like, really we only have a y-axis scale, and that y-axis is energy, which is super important. That has to be labeled. And then at the lowest part, the very like bottom line is our lowest energy. We call it the ground state energy, and it's negative. So this, something to note about these energy scale conventions, 0 is at the top. So everything that we're looking at is like a negative value, and lower energy is usually considered a better thing. So this is why like the kind of like the final states that we end up in, or even if we are doing problems where we have atoms getting excited, we have things going up to higher energies, up to higher states. The like eventuality is that it's going to go back down to a lower energy. It's not going to stay at a higher energy state. And that's also the result, right, that we see in things like a neon sign, right? That output are the photons from when the atoms go back down to their lower energy states. Okay, so we have the lowest energy, the N value. We will call it an N value, and then we're going to use this N value in a later part. So it will mean the same thing. We just don't have to really define it yet, other than to tell you it's the energy level. And that 1 is the lowest. So most negative energy, N equals 1, ground state. The next level up is N equals 2. And we call it it's an excited state because it's higher than the ground state. And if it's the first one, we call it the first excited state. N equals 3 is the second excited state. So this is like, well, I guess it's like with pageant winners, right? The ground state is the person who wins. The person who came in second place is the first alternate. The person who came in third place is the second alternate, right? If that helps you remember it. So this is a pattern. These are the actual energy values in a hydrogen atom. And so something that you'll notice is that as we go up higher in energy, the levels get closer together. So this is a feature, a thing that happens. So we have this. So what would happen, like the process by which you would see a photon emitted from a hydrogen atom, is that I first have this gray line going from the ground state up to the second excited state. So my N equals 3 level. That is putting energy into the atom. It's absorbing that energy from somewhere. It could be absorbing it from a photon. Whatever we need to do. Typically, we're going to talk about it absorbing energy from a photon. So the electron in hydrogen jumps up to the third energy level, which is the second excited state, after absorbing that specific amount of energy. And then it can do a number of things. So it can transition back down to N equals 1. It could go from 3 all the way back down to 1, which I don't have that arrow written on here. Or it could go from 3 to 2 and emit a photon that has that very specific amount of energy. But now my electron is still in the first excited state, so it could then go from N equals 2 to N equals 1 and emit that amount of energy. As long as what happens overall is that the amount of energy that goes in is equal to the amount of energy that goes out. So if it jumped up to N equals 3, and then let's say it jumped down to N equals 2 and emitted that photon, it could not jump back up unless it absorbed more energy from the new photon. A second way that we could show this is by showing this sort of like concentric circle version of an atom structure. So we have the nucleus in the middle, and then the lowest energy level is the one that's closest to the nucleus. So it's my n equals 1, and then I also have, right, the next circle out is n equals 2, the next circle out is n equals 3. And what would happen is that my atom would absorb a photon. That increase in energy would be used to take the electron so it could jump up to, say, n equals 3. And so that's what I have shown in the picture on the right, is my electron now in the n equals 3 level. And then the electron can jump back down, and in the process, it emits a photon. So this is the Bohr model for the atom. It works great for the hydrogen atom. It's not perfectly correct, but our energy levels are calculated very nicely with his equation. So the Bohr equation gives us the energy for any level. And then we also have a put together version to calculate delta E in a little bit. So the energy of any level is negative 2.18 times 10 to the minus 18th joules times z squared over n squared. So z is the same as it was in module 2, way back at this point. It's the atomic number. So it's the number of protons. And n is the level that you are calculating that energy value for. So this works great for any one electron atom. So hydrogen. Or it just has to have one electron. The problem is when we have multiple electrons, they interact with each other. The energy levels get more complicated. There's just a lot more going on. But if I work with cations, it's possible to work with other elements that only have one electron and calculate the energies of these levels for that atom. So hydrogen is great. Helium, if it only has a 1 plus, if it has a 1 plus charge, it would only have one electron. Lithium, well, if it had a 2 plus charge, then it would only have one electron. And then, right, I've got iron as an example here. Now, it's pretty difficult to imagine creating an iron ion with a 25 plus charge to ensure that it only has one electron. But if you could, and if you did, you could use the Bohr equation to calculate the energy levels in that atom. Okay, now for the atom overall, the change in energy, well, we calculate it like we calculate any kind of delta value. It's the final energy minus the initial energy. So if you do that for the Bohr equation, right, where the Bohr equation that we got at first was just for one energy level, if we do it for final and initial, we can factor some things out. Like we don't need to put in the atomic number twice. We don't need to put in this constant twice. And the change in energy for the atom can be calculated with negative 2.8 times 10 to the minus 18th joules times z squared times 1 over the final energy state squared minus 1 over the initial energy state squared. So this is on your equation sheet. We're going to use this a lot. The delta E can be positive or negative. It depends on if you have absorption or emission. So if the atom absorbed a photon, the change in energy will be positive. So absorbing a photon, electron jumps up, delta E is positive. Delta E will be negative if something is emitted. So electron jumps down, photon emitted, delta E for the atom is negative because it's decreasing in energy. Now, the energy of the photon that is absorbed or emitted will be the absolute value of the energy of the atom. So the energy of a photon is always positive. It cannot be negative. If it's negative, you're going to start to get things like negative wavelength, negative frequency, and those values don't make sense to be negative values. So the photon is always positive. The delta E for the atom depends on whether it's emission or absorption. And then we already know how to calculate. things like wavelength and frequency from energy of a photon. So let's practice. We're going to calculate delta E for an atom where we have an electron going from n equals 3 to n equals 2, and it's going to be in a hydrogen atom. So delta E for 3 to 2, and you'll see these subscripts, the 3 going to 2, on the delta E, just to help you keep track of what's final, what's initial, and to kind of set your expectations for whether or not it will be a negative or a positive energy value. So I've got negative 2.18 times 10 to the minus 18th joules. For hydrogen, my Z is 1, so 1 squared. And then in parentheses, 1 over 4. So that's my final energy value squared, so 2 squared, minus 1 over 9, because that was 1 over 3 squared. And out of this, you should try this with your calculator. I got negative 3.03 times 10 to the minus 19th joules. So let's see, I have an electron going from 3 to 2. That means it's going to emit a photon. So a negative energy is correct. Well, and that's the second part of my question. So is the photon emitted or absorbed? It was emitted, which we know because the energy is negative. And then this is asking us to calculate its wavelength. So the energy of the photon will be the absolute value of the delta E of the atom. So my photon energy is positive 3.03 times 10 to the minus 19th joules. And then I've just got the rearranged equation that relates wavelength and energy here. I need hc over the energy, where h is a constant, c is a constant, and then I'm plugging in my energy value. And this would give me 657 nanometers, which is really quite close to that 656 nanometers that we saw in the hydrogen atom example.